Welcome back, folks. I'm Alex. I've been working through Advent of Code 2023, and I am now going through day 3. And I will tell you, day 3 was a rough one. I am currently recording this on day 4 because I spent a chunk of day 3 actually coming up with the solutions for Elixir and Ruby, and yeah, it was kind of a tough one for me. So I'm going to also deviate a bit on this one. I've been doing kind of a coding as I go and talking through what I'm doing while I'm coding. I'm not sure how much value there is in that, and I'm basically recoding solutions I already came up with. So today I'm going to just be going through the code that I came up with and telling you my thought processes and why I chose to do things in certain ways. If you'd rather watch me code and type, then let me know in the comments and I can kind of go back to doing it the old way. For now though, I kind of feel like I can make it a little bit tighter video if I do it this way, and there will be a little less frustration by you folks watching me stumble around when I make typos and don't recreate it exactly the same way and wonder why it doesn't work, etc. Once again, because I'm a day late, I don't have the scotch to drink with you today. It was a scotch. I do have the empty bottle. Not that it does you much good, but this was day 3's bottle. It was a scotch again this time. It was called Banknote, and it's a 5-year peated blended scotch. So it's a blended scotch. It says it's peated. It had a very light peat to it. When you smell it, you just barely get kind of the peatiness in the background. But really, what I got a lot of on both the aroma and the palate was I got some nuttiness. I got some light bit of chocolate. I kind of got some chocolate out of there. There was a bit of fruitiness, kind of a dark fruitiness to it. And there was this very background layer of peat. Maybe gave it a little bit of saltiness, but overall it was, very light. Yesterday's day 2 was peated as well. I said that was a light peat. This one is even lighter. So it was very enjoyable though. I liked drinking it. It was refreshing last night. Let's see. Let's dive into some of the code and talk about where we're at with the problem for day 3. So for day 3, we managed to get to the gondola stations, but the gondolas weren't working, and they need us to help parse information out of these schematics that they've got. And the schematics that they have look like this. They're basically this kind of a grid, if you will, that has some numbers in it, some placeholders that are just periods, and then there's random symbols throughout. Like some of the symbols are an asterisk, some are a pound sign, some are a plus. There's all sorts of different symbols in there. And some of the numbers represent part numbers, and some of the numbers are just in there to waste space, I guess. I don't know. They don't really explain what the other numbers are. But the way this works is they want us to determine which ones are part numbers. A part number is a number that is adjacent to a symbol in some way. So adjacent to a symbol means it has the symbol right next to it, or above or below it, or diagonally even. So for example, 467 is a part number because it is adjacent to this asterisk here. 114 is not a part number because it is not adjacent to anything. 35 is a part number because it's adjacent to the asterisk. 633 is because it's adjacent to the pound sign there. So that's how it kind of works here. And what they describe here is in this kind of mess here, only two of them are not part numbers, 114 and 58. Every other number is a part number. And what they want us to do is find all the part numbers and sum them up. So in this small little example, their sum is 4,361. And what we want to do then is sum up those part numbers, and that'll be the result. So how did I tackle this? Let's jump into Part A's code. So as usual, I use AOC, my little helper module, and then I have my solution that takes in a path. My solution function then sends that path into read lines, and we trim every line. And then what I wanted to do was I wanted to basically create a grid, kind of a two-dimensional array that could be referenced by indices there, by coordinates. And so what I did was I mapped each line of the input into a split that's split on an empty string. So splitting on an empty string will just divide it into all of the characters. I did a trim true just to make sure there's no extra funky space or whatever. And then I wanted to create a grid map. And a grid map for me was this idea that took that input grid and turned it into something that I could more easily reference. So a grid map then took the coordinates, XY coordinates, as the key in a map that would then be a character. So for example, in my map on this example data, I wanted it to be so that if I had the key 0, 0, that would map to 4. And if I had the key 1, 0, that would map to 6. So the first coordinate is the x, which is my spot along the y, this way, and the x-axis, and the y would be down here. My column that my row that I'm on. So my columns are the x, my rows are the y. So that was my goal with create grid map. So my create grid map function basically took the grid, which is that two-dimensional array, and I went over each one of those elements with index, and then I mapped those with a function that took that turned coordinates in to characters. So it mapped the coordinates to the characters. So what does that do? So each one of these ends up getting a tuple that is the row and then the y value. That's what this with index did. So it takes every single row and it gives me the row, which is itself an array of characters, and then the index. And for each row then, I use an index again, because for each row, I want to find out what the index of each character is. Once I have that, I can map that over, and what I'm going to get fed into that function is the character and its x value in the grid. And then I have the y value from up here, and I have the x. So now I can turn that into a tuple that I can then turn into a map if I want here. So the tuple will have the first element of the tuple will be a coordinate, xy coordinate, and the second element of the tuple will be a character. And when that all comes back, it's actually got some extra layering in there from the nested arrays. So I just flatten that, and then I say map.new, and that'll give me the map I was looking for, where I basically have a map that takes a coordinate and gives me a character. That's a lot easier for me to work with as I start thinking about wanting to like look up stuff in that grid that it gave me. There may be another way to do it, but for me, logically, that was the best one. So after we've created the grid map, I want to find all the part numbers. So in this input, there's all these numbers here. Some of them are part numbers, some of them are not. And I basically want to find all of the ones that are part numbers. So in order to do that, we go down here to find part numbers, and it takes in a grid map, that map that I created. And with that grid map, I want to find all the numbers first. So there's a bunch of numbers in the grid map. I want to find all those numbers, and then I'll worry about whether the number is actually a part number. So to find, once I've found all the numbers, then I can filter down and say, hey, which one of these are part numbers? And keep those, so filter those. And then once I have all the part numbers, then I want to map the number that I've got into the number itself. And we'll go over this when I go through these other functions, like where did this come from here? A number and then some second value in the tuple there. We'll go over that shortly here. But the idea is we want to take all those numbers, and now we've got the numbers that are the part numbers, and for each one of those we just want to turn it into an integer. So that'll be, that list will end up being strings like 467, 35. We want to turn those into 467 and 35. That way we can sum them up like we were asked to do. So the first thing we have to do is to find numbers. So let's go down to find numbers. Find numbers takes a grid map, and it filters all of the things in the grid map. The grid map, if you recall, is a large map that takes coordinate into a character. So if we filter that, we're going to filter over the tuple of coordinate character, and we want to keep the ones where it's a number cell. A number cell is basically whenever the character is a digit. So we just use a simple regular expression to check, is this character a digit or not? If it is, great, we want to keep that. It means it is part of a number in our plan. And so that'll give us a result, which is a set of tuples that are a coordinate and a character where we know the character is a digit. It'll throw out everything else. Well, because we want to actually capture those whole numbers that we had in the input, I'm going to sort by the coordinates because I want to make sure that I have all of my pieces in order going across, kind of like you're reading line by line. So it would have x's in order, all for y0, and then it would have x's in order, all for y1, etc. That'll make it easier to then process this list. So sort by coordinate is just fairly simple here. We use the enum.sort, and we give it a function to sort by. And what we're getting in as inputs is two tuples, that is a coordinate and a digit. We don't really care what the digit is. We only really care about the coordinate part of it. So we're getting two of them in because we're comparing two items in the list and to help sort. When the x is the same and the y is the same, then it's the same. So it doesn't need to switch anything around in the sort. When there's different y's, we don't really care about the x. When there's different y's, if the first y is less than the second y, then it should come first. and so we return true. If the y is the same, but the x's are different, if the first x is less than the second x, then we want to return true as well from here. Otherwise, any other time, it doesn't come first, it comes later, and so we return false. And that'll just sort it all out by coordinates, so we'll get what we were looking for going across, down, like that. So now we can do this chunk while, and we're going to abuse the chunk while function a little bit. Chunk while allows us to take an enumerable thing. This is going to be this list of tuples that have a coordinate and a digit in them, and it allows us to create chunks of them. And so if you think about it, what we want to do looking at this input is we'd like to chunk every time we get to a whole number here. And the reason, and the way we'll know that it's a whole number here is these are always consecutive x's, right? So if the y is the same and x is just going up by 1 each time, then it's the same number. And we know that this is going to be different because there's this gap here that you'll see as a gap in the x value that we're dealing with there. So, but we're going to abuse the chunk function a little bit because chunk while is normally supposed to just take the inputs and group them together, right? But we could do that and then do a mapping on it, but because chunk while allows us to emit whatever we want to emit as our accumulator, we're going to actually use it to build up the output that we actually want. So it's a little confusing here, but I hope that it makes a little bit of sense while we walk through there. So chunk while takes a chunking function and a finalizer function. The chunking function is how you determine whether or not to emit a new chunk, and the finalizer function allows you to do any cleanup, because if you have a partial chunk at the end that you didn't emit, then it lets you emit a final chunk or not. And so let's look at the number chunker function first. The number chunker function has two definitions. The first definition here, or actually it has three definitions. The first definition says, hey, if I get an empty tuple as my accumulator and a coordinate and a character as my input that I'm working on, then I want to continue with an accumulator. So I'm not going to emit a chunk yet, because this is actually the start of a brand new chunk. Having an empty accumulator here means that I'm starting a brand new chunk. So I want to continue with a brand new accumulator here that has the character and a list containing the single coordinate there. The next thing I want to match on is, well, what if I get a coordinate and a character out, and I already have an accumulator that's got a number in it and then some list of coordinates, and I have a guard clause here because I'm going to actually peer into the coordinates, and if in the coordinate that I got in, the y is the same as the first coordinate in my list, then I know I'm on the same line. And then if this is my x1 and this is my x2, then if x1 minus y2 equals 1, then I know that I'm right next to it. I'm still contiguous, right? So if I'm contiguous, then it's the same number, and so I want to again emit. I don't want to emit a chunk yet. I want to just keep accumulating But now what I'm going to do is I'm going to stick the character on the end of this number string. So I'm just going to build up that string of numbers, and then I'm going to store the coordinate at the head of this list of coordinates for the number. Finally, we have this final match that says, hey, if I get a coordinate and a character, and then I've got this accumulator, but this other one didn't match first, then I know that I must be at the end. So I'm starting a brand new chunk again. And here I want to go ahead and use the version that returns a tuple with 3 elements in it. Continue, and then the chunk that we are going to emit, which is our number and the set of coordinates, so that'll be emitted into the result. And then we've got the start of a brand new chunk where we're going to return the character and a coordinate. And now that should basically chunk this up into numbers. Our finalizer then needs to deal with, well, what if the finalizer gets an empty accumulator? Well, then we just want to return the accumulator, and we don't want to emit anything because that's just like garbage. If the number finalizer, though, has some stuff in the accumulator, a number and a set of coordinates, then we want to emit that as its final chunk. And so we will go ahead and do a continue and emit that final chunk, and then send out a empty accumulator. So at the end of the day, with this chunk while, the end result means that we will have a list of tuples where each tuple is going to look like a character, which is, or not a character, a number, which is a string representation of a number, and then a list of coordinates. That list of coordinates is useful because when we're looking for the symbols, we need to see if it's anywhere around that number that we're working on. So we need the whole list of coordinates for that number. So that's what that chunk while does. So now that we've found our numbers, now it makes a little bit more sense. When we go to filter, we filter out and we want to find all the part numbers. So when we go to the part number function, it takes in that tuple. We don't really care what the number is, we just care what the coordinates are. And we need this map because we're going to look in the map. We're going to try and find whether there's a symbol near us. And we're going to define a part number as any time the number has a set of coordinates where any of those coordinates is near a symbol. So we've got this other function, near symbol, that does a little check that says, hey, is this coordinate near a symbol in the grid map? And the way we do that is we take in this coordinate, which has an x and a y, and we want to basically create the box around that coordinate because that's going to be the spot that we're going to look for a symbol. So this is just kind of a little tedious little build out here where we go to the left of our x and we leave the y the same. We go to the right of our x and we leave y the same. We keep x the same and we go up on y. We leave x the same and we go down on y. And then we do the diagonals. And so we go back and up, and then we go down and right, and back and up, and back and down. So I may have got that wrong, but we're getting those diagonals, right? So we've got the up, down, left, right, diagonals, creating that little box around the coordinate. And then we want to check if any of those is a symbol in the grid. And so we just have this function symbol, and that takes a coordinate and the grid map, and we basically get the character out of the grid map at that coordinate, or we try to. that character may not exist because we didn't do anything fancy when we were figuring out that box. That box might be outside of the grid in some ways. That's okay though. It'll just mean that's an index that doesn't exist. So when we create the coordinate to look up, it may not actually be in the grid map. And so that's why we check here on the character. If the character we got out is nil, it means it wasn't even on the map in the first place. So that's clearly not a symbol. We can return false. If the character was a period, that's not a symbol. That's just that filler that was in the grid. If the character is a number, so if the regex matches a digit, then we also are not looking at a symbol. We're looking at a number, another piece of the number, and so we return false. Otherwise, if none of those are true, then what we are looking at has to be a symbol. That's the only thing left inside of this grid. So we're going to go ahead and return true in that case. And now we've filtered out and said, okay, this is the part number. It's the numbers that are near a symbol. And finally, we want to map. And again, we have a list that's basically a number and a set of coordinates. Now we don't care about that set of coordinates. We use that set of coordinates to find the whether or not it was next to a symbol. But once we've done that, we don't actually care where the number is anymore. We just want to know what the number is. So we map that into the pure number, and we just do a quick little string to integer on it. So now we've found all the part numbers, extracted them out. We have a list of integers at this point. So now we can go back up to our main function here, our solution. After we found the part numbers, we do an enum.sum, and we sum them all up. Now let's do a little check here, see if that worked the way we expected to. So we will go ahead and pop into IEX, and we will say AOC day 03A dot solution, and we give it the path to our data file. And let's do the check on the test first. So day 03 test.text. 4,361. If we pop over here, we see that it should be 4,361. So we did that right. Perfect. And that means that we can probably trust that if we run this on the full data set, the answer that will give us a star is 554,003. That is part A. That was definitely a little bit tricky for me to figure out. I had to figure out, how am I going to structure the data? How am I going to find those numbers? Once I've found those numbers, how do I determine whether they're near a symbol? It definitely took a while. Overall, in adventofcode, I really hate the ones where they give you a visual map and then expect you to infer stuff out of the visual map. I just don't like those. Maybe it's because I'm not a very visual person. I don't know, but it's always been tricky for me. But let's pop over and let's talk about part B. So let's read what part B says. So part B says, all right, that got the gondola working, but it's going incredibly slow. Turns out that the missing part wasn't the only issue. They also need to get the gear ratios right. And so they need help finding all the gear ratios. So the input is exactly the same as it usually is, but they define a gear as any asterisk. An asterisk is a gear, but it's not always a gear. It's only a gear if it's next to exactly two numbers. If an asterisk is next to one number, it's not a gear. I don't know if there are any in there, but if it's near three numbers, it's not a gear. It's only a gear if it's next to two part numbers. And if it is a gear, then the gear ratio is what happens when you multiply the two part numbers together. And so you multiply those two part numbers, and then that gives you the gear ratio. And what they would like is for us to find all the gears, determine their gear ratios, and then sum up all of the gear ratios. So as you can imagine, a lot of the code is going to end up being very similar. So I'll talk through a little bit about what's different. You already understand how I tackled a lot of the same stuff. So we're going to start out the same way in Part B. In Part B, we're going to take in our input the same exact way. We're going to create the same exact grid map. But instead of finding the part numbers, we're going to find the gear ratios so that we can sum them. So our function for finding the gear ratios still needs to find the part numbers, and it's going to take these part numbers, but it's going to find them a little bit different because I want the raw part number information including the coordinates. So I changed that find part numbers function. Before, it emitted a list of just the part numbers. Now, when I find part numbers, let's see where I put that function there. Find numbers, find part numbers. Let's just go to definition on there. So find part numbers takes in a grid map, we find the numbers, and we filter out the ones that are part numbers. And then in our previous one, we were then taking it a step further and extracting the actual number part, turning it into an integer, but we actually want that tuple that has the part number and then that list of coordinates. That list of coordinates is going to be super important to help determine whether or not it's part of a gear ratio. So back up when we're calculating our gear ratios, we get our part numbers, and then in the grid map, we want to find all the asterisk cells. They may be gears, they may not be gears, but we know that all the gears are asterisks, but not all the asterisks are gears. So the first step is to just find the cells in our grid map that are asterisks. So we filter the grid map, and our function is pretty straightforward. If the character is an asterisk, we return true, otherwise false. And then we check to see the what are the parts for this asterisk. There might be none, there might be one, there might be two, there might be more than two, we don't know, but we want to find all the parts that are, all the part numbers that are near the asterisk. So we call, we map over our asterisks, and we want to turn each asterisk into a list of parts that are near that asterisk. And so we send in the part numbers along with the asterisk itself. So parts for asterisk takes in an asterisk, which we don't care, we know that's an asterisk, so we just ignore it, and we pay attention to the coordinate, and it takes in the part numbers. And for the part numbers, we want to take those part numbers and we want to filter all of those part numbers, and we want to determine if any of them are close to the asterisk that we have. So we've got this coordinate and we want to check, are any of those part numbers close to the coordinate of the asterisk? So we can check part close to coordinate. A part number has a number and a set of coordinates, and then we want to check this coordinate. So we'll go over the coordinates, and if any of them are close to that coordinate, then we'll keep it we'll say, yes, this is a part that's close to the coordinate. And we check if it's close to the coordinate by just taking in two coordinates and checking the absolute value of the difference in x and the difference in y. And if both of those are less than 1, then we know that we are good to go. We are close to that coordinate, and we know that that part number counts. So that will give us a list of parts that are near the asterisk. And we want that list to be exactly 2 to count as a gear. So I could have named this and kind of called it something like is gear or something like that. But instead, I just did an inline little filter here where I said, take in that list of parts, and if the length of that list is exactly 2, then it must be one that we want, and so we keep it as part of our filter function. And finally, we want to then map that, and we want to take each one of those part numbers there, and we want to just multiply them together. So we will multiply them together. That gives us the gear ratio, which is what we were looking for, and then we can sum them up. So again, this one was easier once we had done Part A. So Part A kind of set us up for a lot of this because we were able to reuse a lot of the same data structures and concepts. Being able to think about finding these things was a lot more straightforward. So Part B didn't take me nearly as long as Part A did. So we can pop up here and we can try it out. We can pop onto IEX. And let's go up and try on our test data for Part B. We get 467,835. Looking at Part B, 467,835. So that is correct. So we can just get our star by running it on the full data and plug that in, and we will get our asterisk. And we are good to go on the Elixir side of things. So moving on to Ruby. The Ruby ended up being a little bit different. The past couple of days, my Ruby ended up being kind of the same solution rewritten. It's still kind of that way. However, I'm taking advantage of some things that Ruby gives us. Specifically, because I created this class, day03A, I have a spot where I can just like hold on to state, hold on to information. I don't have to pass all the data around anymore. And so what I ended up doing is defining a number of functions that would basically store information here. So the main function that I have on this class is sum part numbers that will sum up all the part numbers. And this just takes the part numbers and it maps them into the first element of the part number, which is going to be the actual number, and then it's going to 2i that and then sum it up. So I'm using the same kind of data structure. They're lists instead of tuples because Ruby doesn't have tuples, but the numbers in my system are represented by the string representation of the number, comma, and then a list of its coordinates. So we take the first element in that, and then we 2i all of them and sum them up. So what are part numbers? Well, part numbers are all of the numbers, and we select out the ones where it's a part number. Okay, well, what are the numbers? Well, the numbers are, we take our grid map and we select out from our grid map everything from our grid map that is a number. And we just do an array on it to turn it into an array, and then we sort it just like we did before with a cell sorter. I'll go over the cell sorter. And then we use chunk while. Ruby doesn't let us abuse chunk while like Elixir does, so we have to do that method I alluded to in the Elixir that we could have done, where we have to chunk while, and then we have to map to turn it into the result format that we actually want. So let's go through here a little bit. Let's go all the way to grid map since we're talking about grid map. What is grid map? Well, grid map, we can go down here, and grid map again does some memoization here where we just return the grid map if we already grabbed it. Otherwise, I decided to allow for some mutation just because it makes life a little bit easier. So I create a new map or a hash. I create a new hash, and then I go over the grid with index, and then for each row, I go over the row with index, and that gives me the cell, and I have the X and the Y, and then I can create a map a hash that has as its key the coordinate and has as its value the cell. And I'm just sticking it in there rather than building it up. And then finally, I just set my my grid map to this map that I built up. And the grid itself is just reading in from the file the lines and splitting like I did in previous. Again, I'm doing a lot of just like sticking this into variables so that I can have clean code that just references these other functions that are basically these memoized values. So let's go back up. We were talking about how do we find our numbers. So we've got our part numbers. We want to select out anywhere where there are part number, and it's a part number when we tear apart the number and say these coordinates, if any of them are near a symbol. And if they're near a symbol, we basically do what we did in the Elixir, where we figure out the coordinate, the x and y, and we build up this list that's the box around it, and we check if any of those are a symbol. And we just check to see if it's a symbol by looking in the grid map. And we don't have to, unlike the Elixir where we had to pass the grid map in, Ruby, we can just call grid map because that's in the class that we've got. We already defined what grid map is, so we can just call grid map and use it. And the logic is basically the same. If it's nil, then we don't want it. If it's a period, if it's a digit, we don't want it. Otherwise, it must be a symbol, and we return true out there. And that's how we find all of our part numbers. The determining the numbers themselves is a little bit different. I want to go over the chunk while and the sorter. So the sorter is a little bit different because Ruby sorters act a little bit different than the sorter function I used in Elixir. So in Elixir, in Ruby, when I do the sorter, a cell sorter, it takes two cells, cell 1 and cell 2. Each cell is a coordinate and then its contents, a coordinate and its contents. I don't really care about the contents here, I'm just caring about the coordinates. So I pull out the coordinates, I pull out the x, y, and then I do the same kind of comparison that I did before. Only now I'm returning a 0 if it's the same, -1 if it comes before, 1 if it comes after. So it's the same if the x's are the same and the y's the same. It's before if the first y is less than the second y. It's before if the y's are the same but the first x is less than the second x. And otherwise it's after. So we return a 1. So that's how our sorter works. Our chunker basically says chunk while we have contiguous digits. So it's kind of the same thing that we were doing before, but instead of doing that transform like we were doing in the Elixir function, we're just going to check in the chunker in Ruby gives us two cells and says, hey, should I make a chunk here, right? I've got what would be the end of a chunk if you want me to chunk, and the beginning of a new chunk if you want me to chunk, or should I keep them together in the same chunk? And so it gives me two cells and says, hey, what should I do? Should I do a chunk or not? So it's true or false. If it's supposed to do a chunk, I emit true. If I want to keep it the same and keep building the chunk, then I return false. So I basically check, I pull the coordinate out of each cell, and I pull the x's and y's out of each coordinate, and then if the y is the same and the x's are next to each other, then then this is true, and it's, I guess when you're true, you want to keep building the same chunk. When you're false, you want to emit a chunk and then start over again. So we're emitting true here if we want to keep going on the same chunk because these numbers are next to each other. And then that just gives us the chunked values, but we want to turn them into that other format. So I map into this number with coordinates where I take a chunk and we reduce the chunk down over this idea of a list that's got an empty string and an empty list of coordinates, and our goal is we want it to be a string representation of a number and a list of coordinates. And we do that by basically pulling the coordinate and the digit out of the cell, and then we pull the number and the coordinates out of our memo device here, and then we just add on to the number string the digit string. So we just tack the digit onto the end of the number, and we push our coordinate onto the list of coordinates. And that's how we will kind of restructure this into that same format that we had in Elixir, only slightly different because we're using arrays rather than tuples. Basically the same idea though. So then finally, now that we've got all of that, you can see how when we pull out from the numbers all of the part numbers, we can then map and take the first piece off and turn it into an integer and sum it up. And that's how we get the sum of all of our part numbers. And we can see that works the same by going up and bin console. We'll say AOC day 03a.new. Let's capture this into a solution. In our data directory, day 03 test.text, solution.sum part numbers. 4361, that sounds awful familiar. Is that what we were looking for? 4361, it is. So I'm pretty confident that if we run this again on our full data, then we will get the answer that gives us a star. Perfect. Very cool. So let's go through part B. Part B ends up looking very similar, just like in the Elixir side, but we're going to do these gear ratios here. So our main function here is sum the gear ratios, and we do that by taking our gear ratios and summing them. Well, what are our gear ratios? Again, we do this little memoization, and we take our grid map and we select out all of our asterisks. Asterisk is just defined just like we did in Elixir, where the character is a star. And then we want to find the parts for each asterisk cell. We want to find the parts for that asterisk. So the parts for the asterisk takes in an asterisk cell, and it pulls out the coordinate. We don't care about the asterisk itself. And then it cycles over all of the part numbers. Again, we can just talk about part numbers because we have that memoized value for part numbers. And we're going to select out all of the part numbers where the part is near the coordinate. And when we have those, then we map over those, and we want to take out the actual number part of the part number, turn it into an integer, and return that out. And down here in we want to check if a part number is near a coordinate. We take in the part and the coordinate. We pull the coordinate list out of the part, and then we check if any of those coordinates in the list are near that coordinate. And our logic ends up being the same as it was in Elixir, where we take two coordinates and determine if they're near each other. by just taking the absolute values of the x's and y's and seeing if it's just a difference of one or less for both of those. That means they're next to each other, and we call that good enough. So that's how we determine if the part is part of the asterisk. And that'll return a list of numbers because we did this little conversion down here into integers. So we have a list of numbers, and we want to basically select out the ones where the list is a length of 2. So a gear is a gear if it has 2 part numbers exactly next to it. So we'll pull that out, and then we map that into a gear ratio. A gear ratio simply just takes the parts, which is a list, pulls part 1 and part 2 out and multiplies them together. And once we've multiplied them together, that's the gear ratio. It gets returned as part of that list of gear ratios, and then we just sum them up. So that all fell together pretty quickly and easily, and we can go back over here and we can say our solution this time is off of our test file with B. And we want to sum the gear ratios. And that looks right. Let's check part B. Yes, we are right. So we can get our star with Ruby if we want by using the full test file. And we would plug that in and get a star. So I hope this format where I'm just explaining the code maybe is a little less daunting than me going through and actually typing it all out. For one thing, everything just worked when I was showing it off to you, and hopefully I was able to explain the code in a cohesive, coherent way that you were able to understand. I'm going to try this format again when I do day 4, but definitely please leave some comments if you'd rather me go back to the other way. Thank you so much for watching, and I hope some of this has been educational.